The year is 1945. Berlin lies in ruins, its grand boulevards reduced to rubble, its proud monuments shattered by war. In a quiet corner of what remains of Germany, an elderly man stands beside a fresh grave. His name is Max Planck, and he has just buried his son. Erwin Planck was 47 years old when the Gestapo executed him. His crime? Opposing Hitler. His father, now 77, had pleaded for mercy, had used what remained of his once considerable influence in German scientific circles, had written letters that went unanswered. None of it mattered. The regime that had torn Germany apart took one more life before its own collapse. This is Max Planck's fifth child to die. Before we jump back in, tell us where you're tuning in from, and if these history tales fascinate you, make sure you're subscribed, because tomorrow I've saved something extra special for you. Consider what it means to lose a child. Now imagine losing 5. First Marie, his eldest daughter, died from tuberculosis in 1909. The disease consumed her slowly, and Max could only watch. Then came the Great War, and his son Karl, a young soldier full of promise, fell at Verdun in 1916. The following year, Grete died giving birth. 2 years later, Emma, his other twin daughter, died the same way in childbirth. And now Erwin, executed for having the courage Max himself possessed in his work, but which had cost his son everything. 4 of his 5 children, gone. His first wife, gone. The Germany he knew, the one of music and mathematics and midnight discussions about the nature of reality, gone. Yet this man, this gentle physicist who has endured more tragedy than most could bear in 10 lifetimes, gave humanity its greatest intellectual revolution, the quantum theory, the discovery that changed everything we know about reality itself. How does a life filled with such darkness produce the light that illuminates our modern world? How does personal catastrophe prepare a soul to shatter 300 years of scientific certainty? To answer these questions, we must go back to a problem that threatened to unravel all of physics, back to a crisis that brilliant minds fled from in terror, back to the black-body radiation problem. In the final months of 1899, physics stood on the edge of an abyss. For 2 centuries, since Newton had revealed the elegant mathematics governing motion and gravity, the physical sciences had marched forward with confident precision. Light behaved as waves. Energy flowed continuously. The universe operated like a vast, predictable machine. Every phenomenon could be calculated, every mystery eventually solved. Then came the problem of heated objects. When you heat a piece of metal, it glows. First red, then orange, then yellow, then white as the temperature rises. This much had been known since humans first worked with fire. But why? What determined which colours an object? Emitted at which temperatures? It seemed like such a simple question. Surely the established laws of physics could explain it. They could not. Physicists created what they called a black body, a theoretical perfect absorber and emitter of radiation. Imagine a hollow cavity with a small hole, like an oven with a tiny opening. Heat this cavity, and radiation pours out through the hole. The question was simple. How much energy emerges at each wavelength as temperature changes? The classical equations said something impossible. They predicted that infinite energy should pour out at shorter and shorter wavelengths. Heat a black body to any temperature, and according to Maxwell's electromagnetic theory and the principle of equipartition of energy, it should emit ultraviolet radiation of unlimited intensity. Every oven should flood the universe with infinite energy. This was called the ultraviolet catastrophe, and it threatened everything. Brilliant physicists attacked the problem. Wilhelm Wien developed an equation that worked at high frequencies, but failed at low ones. Lord Rayleigh and James Jeans created a formula that succeeded at low frequencies but produced infinity at high ones. The more they calculated, the worse it became. The mathematics that had explained every other phenomenon in physics simply broke down. By the autumn of 1899, many physicists were ready to abandon the problem entirely. Some suggested that perhaps the classical laws needed minor adjustments. Others wondered if something fundamental was wrong with their understanding of energy itself. Most simply moved on to problems that could actually be solved. But not Max Planck. In his laboratory in Berlin, Planck sat surrounded by calculations. He held the chair once occupied by Gustav Kirchhoff, one of the giants of 19th century physics. Kirchhoff had been obsessed with this blackbody problem before his death. Now it belonged to Planck, this methodical, careful man who approached physics with the precision of a master craftsman and the patience of a monk. For a decade, he had worked on thermodynamics, that branch of physics dealing with heat and energy, while other physicists pursued the glamorous problems of electromagnetism or sought to understand the newly discovered X-rays and radioactivity. Planck laboured in obscurity on the fundamentals. He studied entropy, that mysterious quantity measuring disorder. He wrestled with the second law of thermodynamics, which declares that entropy always increases, that the universe tends toward chaos. There was something almost philosophical about his approach. While others raced for quick results and dramatic discoveries, Planck sought deeper principles. He believed that beneath the apparent complexity of nature lay simple, universal truths. He had faith in the orderliness of the universe, in its mathematical elegance. This faith would be tested. At home, his life was full. His wife Marie was his anchor, his partner in all things. Their children filled the household with music and laughter. Max himself was an accomplished pianist, and evenings often ended with the family gathered around the piano, Bach and Brahms flowing through their Berlin home. Karl, his son, showed promise in everything he touched. The twin daughters, Grete and Emma, were inseparable. Young Erwin was bright and curious, and Marie, his eldest daughter, had his own love of learning. But in his study, alone with his equations, Planck faced the blackbody problem that had defeated everyone else. He tried everything the classical theories allowed. He manipulated Maxwell's equations in every conceivable way. He applied thermodynamic principles with increasing desperation. Nothing worked. The mathematics kept leading to the same impossible conclusion: infinite energy at short wavelengths. By October of 1900, Planck was exhausted. He had spent 5 years on intensive calculations, 5 years of failure. His papers piled up, covered in crossed-out equations and discarded approaches. He was 52 years old, and his greatest work seemed destined to be nothing more than an elaborate documentation of defeat. Then, in a moment of desperation, he tried something radical. What if energy didn't flow continuously? What if, instead of being infinitely divisible like water poured from a pitcher, energy came in discrete packets, individual units, chunks, quanta? The idea was absurd. Everything in classical physics assumed that energy was continuous. You could have any amount of energy you wanted, just as you could have any amount of water. There was no minimum unit, no smallest possible quantity. Energy flowed smoothly, gradually, without interruption. But what if it didn't? Planck performed a mathematical trick. He divided energy into finite elements, tiny packets, intending to make the mathematics easier, and then let these packets shrink to zero at the end of his calculation, returning to the continuous flow everyone knew was correct. It was just a temporary assumption, a computational convenience. Except when he worked through the mathematics, something extraordinary happened. The equation worked perfectly. It matched the experimental data at all wavelengths, at all temperatures. The ultraviolet catastrophe vanished, but only if the energy packets didn't shrink to zero, only if they remained finite, only if energy truly came in discrete, indivisible units. Planck stared at his result. He checked his calculations again and again, searching for an error. There was none. The equation was correct, but it required something that contradicted everything physics had established since Newton. On October 19th, 1900, Planck presented his formula to the German Physical Society. He wrote it on the blackboard, this simple equation that described how much energy a black body emits at each wavelength at any temperature. The scientists in attendance recognized immediately that it worked. The fit with experimental data was perfect, but Planck didn't tell them about the quanta, not yet. He had the right formula, but he didn't understand why it was right. He spent the next 2 months in a fever of calculation, trying to derive this empirical formula from first principles, trying to understand what it meant. December 14th, 1900. The date would mark the birth of quantum mechanics, though no one knew it at the time. Planck stood before the German Physical Society once more. His hands trembled as he presented his findings. Energy, he explained, is not continuous. It comes in discrete packets. For electromagnetic radiation of a given frequency, there is a minimum energy unit. Light of a certain color cannot have just any energy. It must have energy equal to a constant multiplied by its frequency. He wrote the equation E equals h times frequency. That constant, h, was a new fundamental constant of nature. Planck calculated its value, 6.626 times 10 to the minus 34th joule seconds. An impossibly tiny number, so small that in everyday life, energy appeared continuous, because these individual packets were far too small to detect. But at the atomic scale, in the world of heated cavities and electromagnetic radiation, this graininess of energy became crucial. Planck's constant. This number would become as fundamental to physics as the speed of light or the gravitational constant. It represented something profound. The universe's fundamental unit of action, the quantum of action. Below this scale, nature refused to operate smoothly. Reality itself was granular. The scientists in attendance understood the mathematics. They appreciated that Planck had solved an intractable problem, but few grasped the revolutionary implications. Planck himself hoped he was wrong. For months afterward, he tried to undo his discovery. He searched desperately for a way to derive the blackbody formula without assuming quantized energy. He wanted to show that energy was really continuous after all, that the quanta were just a mathematical convenience. He failed. Every approach led back to the same conclusion. Nature refused to be continuous. In the privacy of his study, Planck must have wrestled with what he had done. This man who believed in order, in the elegant simplicity of natural laws, had introduced a fundamental discontinuity into physics. This man who approached science with almost religious reverence had shown that at its deepest level, reality was not smooth but lumpy, not flowing but jumping. Yet life continued. His children grew. He played his piano. He walked through Berlin streets, taught his classes, attended conferences. The world around him operated by the old classical laws. Apples fell, light travelled in waves, energy flowed. His discovery seemed almost irrelevant to everyday existence. But in the invisible realm of atoms and radiation, everything had changed. 5 years later, in 1905, a young patent clerk in Switzerland named Albert Einstein read Planck's paper. Einstein was working on the photoelectric effect, another problem that defied classical explanation. When light strikes certain metals, it ejects electrons. But strangely, the energy of these electrons depends on the light's frequency, not its intensity. Brighter light produces more electrons, but not more energetic ones. Only higher frequency light increases their energy. Einstein seized upon Planck's quanta. What if light itself came in packets? What if electromagnetic radiation wasn't really a wave but a stream of particles, each carrying energy equal to h times frequency? These light quanta, later called photons, explained the photoelectric effect perfectly. Planck was horrified. He had quantized energy reluctantly, hoping it was just a mathematical peculiarity of matter's interaction with radiation. But Einstein was quantizing light itself, the thing that propagated through space, the phenomenon Maxwell's wave theory had explained so beautifully. This was too much. Yet the evidence supported Einstein. The photoelectric effect's strange properties made sense only if light came in quanta. The revolution Planck had started was accelerating beyond his control. Other physicists began to notice. By 1913, Niels Bohr used Planck's constant to explain atomic structure. Atoms didn't collapse, Bohr showed, because electrons occupied discrete energy levels, quantum states. They couldn't spiral gradually into the nucleus because there were no intermediate energies available. They had to jump between levels, emitting or absorbing photons of specific energies. The quantum was spreading through physics like wildfire. But for Planck, the personal cost was mounting. His daughter Marie died of tuberculosis in 1909. She was 28. Planck, who had unlocked the secrets of atomic-scale energy, could do nothing as disease consumed his child. All his knowledge, all his understanding of nature's deepest laws was useless against the microscopic organisms destroying her lungs. Then came the Great War. In 1914, Europe descended into mechanized slaughter. Planck, like many German intellectuals, initially supported his country, but as the war ground on, as the casualties mounted, as civilization tore itself apart, his patriotism turned to horror. In 1916, at the Battle of Verdun, Karl Planck fell. Max's son, bright and full of life, became one of 300,000 men who died in that hellish months-long artillery bombardment. A letter arrived at the Planck home. Karl was gone. The following year, 1917, Grete died in childbirth. Then, impossibly, in 1919, Emma died the same way. The twin daughters, inseparable in life, united in the manner of their deaths. Max Planck, the man who had revealed the quantum nature of reality, who had shown that energy comes in discrete, calculable packets, could not calculate his way out of grief. 4 children dead. His wife Marie, worn down by tragedy, died in 1909. He remarried, seeking solace, but the losses accumulated like snow, each one making the burden heavier, and through it all, the quantum revolution continued. Young physicists, born after Planck's initial discovery, pushed the theory into stranger and stranger territory. In 1925, Werner Heisenberg, only 23 years old, created matrix mechanics while recovering from hay fever on the island of Helgoland. In 1926, Erwin Schrödinger developed wave mechanics, showing that particles behaved like waves and waves like particles. The uncertainty principle emerged. You cannot know both a particle's position and momentum with arbitrary precision. The act of measurement affects what you measure. Reality at the quantum scale is fundamentally probabilistic, not deterministic. Einstein hated this. God does not play dice with the universe, he declared. But Bohr countered that it was not our place to tell God how to run the universe. At the 1927 Solvay conference in Brussels, these titans battled over the meaning of quantum mechanics. Einstein proposed thought experiment after thought experiment trying to prove the theory incomplete. Bohr refuted each one. Planck watched his scientific children surpass him. The revolution he had started reluctantly now dominated physics. Every major discovery in atomic and subatomic physics depended on his constant, that tiny number he had calculated in desperation in 1900. But as physics advanced, Germany declined. The Weimar Republic struggled. Economic chaos gave way to political extremism. And then the Nazis came to power. Planck, now in his 70s, held enormous prestige in German science. He had won the Nobel Prize in 1918. He was president of the Kaiser, Wilhelm Society, Germany's premier scientific organization. He used what influence he had to protect Jewish scientists from the regime's increasingly vicious persecution. It wasn't enough. Einstein fled to America. Max Born fled to Britain. Many of Germany's greatest scientific minds scattered across the world, refugees from the madness consuming their homeland. Planck stayed, hoping his presence might preserve something of German science and might protect those who couldn't leave. His son Erwin, working in the German civil service, became involved in the resistance. After the failed July 20th, 1944 plot to assassinate Hitler, the Gestapo arrested everyone even tangentially connected. Erwin Planck had known some of the conspirators. Max pleaded for his son's life. He wrote letters. He called in every favor he had accumulated in 40 years of scientific eminence. Nothing worked. The regime that had destroyed German science, that had driven away the very people who Paul could have given Germany dominance in the emerging nuclear age, took one more thing from the elderly physicist. On January 23, 1945, the Gestapo executed Erwin Planck in Plötzensee prison. Berlin fell to Soviet forces less than 4 months later. The Third Reich collapsed. Hitler killed himself in his bunker. The nightmare ended. But for Max Planck, standing beside his son's grave, the cost was incalculable. 5 children dead, a civilization destroyed. And yet, somehow, through all this darkness, he had given humanity the light of quantum understanding. His constant, born from desperate calculation, had become the key to unlocking atomic energy, to explaining how stars shine, to understanding the very nature of reality. How does tragedy and triumph coexist in one life? How does personal suffering lead to universal insight? These questions have no easy answers, but Max Planck's story suggests something profound about the human capacity to create meaning, from chaos, to find order in the midst of disorder, to discover fundamental truths even as personal foundations crumble. The quantum revolution he started would eventually put computers in our pockets, would enable the technologies that define our modern world. But in 1945, that future was still unimaginable. All Max Planck could see was loss. Yet he did not break. He did not surrender to despair. The same determination that kept him working on the black body problem when everyone else gave up now sustained him through grief that would have destroyed most people. Because Max Planck understood something at a level deeper than words. He understood that beneath the chaos and tragedy of human existence, beneath the apparent randomness of life and death, there were fundamental patterns, universal laws, mathematical truths that remained constant even as everything else changed. His constant, that impossibly tiny number, was one such truth. And though it could not save his children, could not prevent war, could not stop the Nazis, it represented something eternal, a fact about reality that would remain true long after all of human civilization had turned to dust. In the quantum realm, Planck discovered, energy comes in discrete packets. Reality is fundamentally uncertain. The universe operates on probability rather than determinism. These insights contradicted everything physics had taught for 3 centuries, but they were true, irrevocably, experimentally, mathematically true, and that mattered. In a life filled with senseless loss, with tragedy that defied explanation, the existence of such truths provided a foundation. Not comfort, perhaps, but meaning, purpose. The darkness in Max Planck's life was real. The losses were genuine and irreparable. But from that darkness emerged light. Not metaphorical light, but actual understanding of how light itself behaves, how energy works, how atoms function, how the universe operates at its most fundamental level. This is the paradox at the heart of scientific discovery. Progress often comes from crisis. Understanding emerges from confusion. The blackbody problem nearly destroyed physics, but solving it created quantum mechanics. Personal catastrophe nearly destroyed Max Planck, but perhaps that very experience of enduring the unendurable gave him the fortitude to embrace an idea that violated every physical intuition. We cannot know what went through his mind as he stood beside Irwin's grave in 1945, but we can know what he discovered in 1900, and we can trace the line from that discovery to the modern world, to the quantum technologies that now shape human civilization. The story of quantum mechanics is often told as a triumph of human intellect, a sequence of brilliant insights that revealed nature's secrets, and it is that. But it is also a story of human endurance, of continuing to work and think and discover, even when life offers nothing but loss. Max Planck gave us the quantum, but perhaps more importantly, he showed us that the search for truth can sustain the human spirit even in the darkest times. That understanding itself is valuable, regardless of personal cost. That some things are worth discovering even if the discovery brings no comfort. The quantum revolution was born in darkness, from the ultraviolet catastrophe that threatened to break physics, from the desperate calculations of a man who would lose almost everything, came the light that illuminates our modern understanding of reality. And that light still shines. To understand how Max Planck became the man who would revolutionize physics, we must travel back to his beginning, to a world before quantum mechanics, before relativity, before anyone imagined that the classical certainties of Newtonian physics could be overturned. The year is 1858. In the city of Kiel, on Germany's northern coast where the Baltic Sea meets the land, a child is born to Johann Julius Wilhelm von Planck and his second wife, Emma Patzig. They name him Karl Ernst Ludwig Marx Planck, though history will know him as Max. His father is a professor of law at the University of Kiel, a man of learning and culture. The Planck household is filled with books and music, with the earnest conversations of academics and the laughter of children. Young Max grows up in an environment where intellectual pursuits are valued above all else, where the life of the mind is considered humanity's highest calling. But these are turbulent times for the German states. Max is only 6 years old when Prussia goes to war with Austria in 1864, fighting for dominance over the collection of kingdoms and principalities that might one day become a unified Germany. The battles are brief but transformative. Prussia wins decisively, and the balance of power shifts. In 1867, when Max is 9 years old, his father accepts a position at the University of Munich. The family moves south, from the windswept coast to the alpine foothills of Bavaria. Munich is a different world. Where Kiel was austere and Protestant, Munich is Baroque and Catholic, a city of ornate churches and beer halls, of art and music and southern German warmth. For young Max, the move is pivotal. Munich's schools are excellent, its Maximilian Gymnasium, one of the finest in Germany. Here, Max encounters a teacher named Hermann Müller, who recognizes something in this quiet, methodical boy, an aptitude for mathematics, a love of logical structure, a mind that seeks patterns and principles beneath surface complexity. Müller teaches Max about energy conservation, about how energy can change form but never disappear. The principle fascinates the young student. Here is a universal law, something that holds true always and everywhere. No matter what happens in the universe, energy remains constant. It transforms from potential to kinetic, from chemical to thermal, but the total never changes. This idea of fundamental conservation laws captures Max's imagination. Beneath the chaos of everyday events, beneath the complexity of natural phenomena, there are simple, inviolable rules. The universe operates not by whim, but by law, and these laws can be discovered through mathematics and careful thought. But Müller also tells young Max something else. He tells him that physics is essentially complete. The great discoveries have been made. Newton's laws explain motion. Maxwell's equations explain electromagnetism. Thermodynamics explains heat. The fundamental structure of physical reality is understood. There might be minor details to work out, small corrections to make, but the edifice is built. The great age of physics is over. For many students, this would be discouraging. Why pursue a field where everything has already been discovered? But Max Planck hears this differently. He hears that physics has achieved something remarkable. It has uncovered eternal truths about nature. And Max wants to understand these truths, to master them, to see for himself the elegant mathematical structures that govern reality. He is not drawn to physics for fame or glory. He seeks something deeper, order, certainty, the satisfaction of understanding how the world works at its most fundamental level. At 16, Max enters the University of Munich to study physics. His professor, Philipp von Jolly, echoes Müller's assessment. The great theoretical work is finished, Jolly tells him. Perhaps experimental physics might offer some opportunities, measuring physical constants with ever greater precision, but the laws themselves are known. Choose a different field, Jolly advises. Mathematics, perhaps, or engineering, somewhere with problems left to solve. But Max persists. If physics is complete, then all the more reason to study it, to master this completed structure, to see the finished cathedral of human understanding about the physical world. He is not looking to make revolutionary discoveries. He wants to contribute to the edifice, to add his small stone to the great building others have constructed. After a year in Munich, Max travels north to Berlin, then the undisputed center of German physics. Here, at the Friedrich Wilhelm University, he attends lectures by the greatest physicists of the age. Hermann von Helmholtz, who formulated the conservation of energy. Gustav Kirchhoff, who developed the laws of spectroscopy and radiation. Berlin in the 1870s is electric with intellectual energy. Germany is newly unified under Prussian leadership. The Franco-Prussian War of 1870 to 1871 has established German military and cultural dominance in Europe. The new German Empire is building universities, funding research, establishing itself as a center of learning to rival any nation on earth. Max studies with dedication. He attends lectures, works through problems, masters, Maxwell's, electromagnetic theory, and Clausius's thermodynamics. But he is not a flashy student. He does not dazzle his professors with brilliant insights. He is thorough, methodical, patient. He checks his calculations twice, 3 times. He seeks to understand deeply rather than quickly. In Berlin, Max encounters the work of Rudolf Clausius on entropy and the second law of thermodynamics. This law states that in any closed system, entropy, the measure of disorder, always increases. Heat flows from hot to cold, never the reverse, without external work. Ordered energy degrades into disordered heat. The universe tends toward equilibrium, toward maximum entropy, toward what physicists call the heat death. This fascinates Max. Here is another universal principle, but one tinged with melancholy. The universe is running down. All the complex structures around us, the stars and planets, life itself, are temporary departures from equilibrium, destined eventually to dissolve into uniform, featureless, thermal chaos. Yet within this bleak vision, Max sees something beautiful. The second law is absolute. It applies to everything, everywhere, always. It is a fundamental constraint on physical reality. And Max wants to understand why. Not just that entropy increases, but what entropy fundamentally is. What is this quantity that always grows? He chooses thermodynamics for his doctoral work, not the glamorous electromagnetism that Maxwell has just unified with optics, not the exciting new field of spectroscopy where Kirchhoff is discovering that different elements emit characteristic patterns of light, but thermodynamics, the study of heat and energy transformation, the graveyard of academic careers, some call it. The important work is done. The field is mature, perfect, Max thinks. Let others chase novelty. He will master the foundations. In 1879, at age 21, Max completes his doctoral dissertation on the second law of thermodynamics. His thesis explores the relationship between entropy and temperature, developing mathematical formulations of Clausius's principles. It is solid work, careful and thorough, but not groundbreaking. His examiners approve it without enthusiasm. Max returns to Munich and completes his habilitation, the qualification needed to become a university lecturer in the German system. For 5 years he teaches at Munich, giving lectures on thermodynamics and mathematical physics to small groups of students. He publishes papers on thermodynamic equilibrium, on the nature of entropy, on the subtle questions surrounding the second law. The work is obscure. Few people read his papers. Thermodynamics is considered a dead end, a finished field. But Max is content. He is building his understanding, block by block, equation by equation. He is learning to think about energy and entropy with the kind of depth that comes only from years of patient study, and he is learning something else, something that will prove crucial later. He is learning that the second law of thermodynamics is statistical in nature. The increase of entropy is not absolute but probabilistic. It is overwhelmingly likely that entropy increases, but not strictly certain. In principle, heat could flow from cold to hot. It is just monumentally improbable. This insight, that a fundamental law of physics might be statistical rather than deterministic, plants a seed in Max's mind. He does not yet know how important this seed will become. In 1885, Max receives an offer. The University of Kiel, his birthplace, wants him as an associate professor. It is not a prestigious position. Kiel is a small university far from the centers of German physics, but it is a real appointment, a chance to establish himself. Max accepts. He moves back to the northern coast, to the city where he was born, and something else happens in 1885. He meets Marie Merck. Marie is the daughter of a Munich banker. She is intelligent, cultured, musical. In a different era, she might have pursued her own academic career, but this is 1885, and such paths are closed to women in Germany. Instead, she brings her considerable intellect to partnership with Max. They marry in March of 1887. Max is 28, Marie is 22. They are deeply compatible. Both love music, both value intellectual pursuits, both seek a life of quiet contemplation rather than social prominence. Within a year, Marie gives birth to their first son, Karl. Then come the twin daughters, Grete and Emma, in 1889. A second son, Erwin, arrives in 1893, followed by another daughter, also named Marie, after her mother, in 1885. Wait, let me correct that. Little Marie is born in 1895, not 1885. 4 children in 8 years, and a household filled with the chaos and joy of young family life. Max proves to be a devoted father. Despite his rigorous work schedule, he makes time for his children. He plays piano for them. He takes them on walks through Kiel's streets, explaining the clouds, the stars, the physics of everyday phenomena. He wants them to see what he sees, a world governed by elegant laws, a universe that makes sense. But Max's career is stagnating. He is 30 years old, publishing steadily in thermodynamics, yet making no impact on the wider physics community. His papers are technically sound but unexciting. He is becoming known as a solid, reliable, but unimaginative physicist, the kind of man who fills teaching positions adequately but will never advance the field. Then, in 1889, opportunity arrives. Gustav Kirchhoff, the great physicist in Berlin, dies. His chair at Friedrich Wilhelm University becomes vacant. Berlin needs someone to fill this prestigious position, someone to carry forward Kirchhoff's work on thermodynamics and radiation. The position is offered to Ludwig Boltzmann, Austria's leading theoretical physicist. Boltzmann declines. It is offered to Heinrich Hertz, who has just experimentally confirmed Maxwell's prediction of electromagnetic waves. Hertz also declines, preferring to stay in Bonn. The Berlin faculty considers other candidates. They need someone competent in thermodynamics, someone who can teach classical physics well, someone reliable, if not brilliant. They consider Max Planck. In 1889, the University of Berlin offers Max the position. He accepts immediately. At age 31, he moves back to Berlin with his young family. He is now professor of theoretical physics at Germany's premier university, holder of Kirchhoff's chair, responsible for training the next generation of German physicists. And he inherits Kirchhoff's obsession, the black-body radiation problem. Kirchhoff had defined the problem clearly. A black body is a perfect absorber and emitter of thermal radiation. The question is, what is the mathematical relationship between the amount of radiation emitted, its wavelength, and the temperature of the black body? This seems like an esoteric question, relevant only to specialists. But it is actually fundamental. Every object emits thermal radiation. Understanding this radiation means understanding how energy flows through the universe. The sun emits radiation that powers all life on Earth. Stars shine because of radiation. The cosmic microwave background that fills the universe is thermal radiation left over from the Big Bang. Get the black-body radiation formula right, and you unlock something profound about how energy and matter interact. Kirchhoff tried and failed. So did Wien, Rayleigh, Jeans, and a dozen other brilliant physicists. The problem had become infamous. A graveyard, not just of careers but of established theories. Classical physics, which worked everywhere else, simply failed here. Max Planck, the methodical, careful physicist who chose thermodynamics because it was safe and complete, has just inherited the one problem that threatens to prove thermodynamics incomplete. He does not yet know this will consume the next decade of his life. He does not yet know this problem will force him to abandon every certainty he has relied upon. He does not yet know that solving it will make him the most revolutionary physicist since Newton. In 1890, Max settles into his new position in Berlin. He teaches courses on mechanics, thermodynamics, and electromagnetism. He supervises doctoral students. He attends faculty meetings and scientific conferences. He takes his place among the physics establishment, and in his study he begins to work on the blackbody problem. At first it seems straightforward. Apply the laws of thermodynamics to electromagnetic radiation. Calculate the equilibrium distribution of energy among different wavelengths. Derive the formula, but the calculations do not work out. The equilibrium, according to classical statistical mechanics, should distribute energy equally among all possible modes of oscillation. This is the equipartition theorem, a fundamental result of thermodynamics. Every degree of freedom should have the same average energy. The problem is that electromagnetic radiation has infinitely many degrees of freedom, an infinite number of possible wavelengths. If energy is distributed equally among them, the total energy becomes infinite. Every heated object should radiate infinite power at short wavelengths. This is the ultraviolet catastrophe, and it is not a minor theoretical inconvenience. It is a fundamental breakdown of physics. Max tries every approach he can think of. He manipulates the thermodynamic formulas. He applies different statistical assumptions. He considers whether the cavity walls might introduce some constraint. Nothing works. Years pass. 1891, 1892, 1893. His children grow. Carl starts school. The twins learn to read. Young Erwin babbles his first words. Marie is born. Life flows on while Max struggles with equations that refuse to cooperate. In 1896, Wilhelm Wien proposes an empirical formula. It fits the experimental data at short wavelengths but fails at long ones. It is not derived from first principles but simply guessed and adjusted to match measurements. Max respects Wien's work but knows this cannot be the final answer. Physics needs to understand why the formula works, not just that it does. In 1899, Lord Rayleigh and James Jeans derive a formula from classical principles. It works at long wavelengths but predicts infinite energy at short wavelengths, the ultraviolet catastrophe in its purest form. Max is now 41 years old. He has spent 9 years on this problem. 9 years of failed approaches, discarded calculations, dead ends. His publications accumulate but solve nothing. He is becoming known as the physicist who cannot solve the black-body problem, the man stuck on Kirchhoff's impossible puzzle. At home, he plays Bach on his piano. The well-tempered clavier, the Goldberg variations, those mathematical constructions of sound that Bach built with architectural precision. The music is complete, perfect, finished. Every note in its proper place, every voice interweaving according to strict rules that somehow produce transcendent beauty. Why cannot physics be like this? Max wonders. Why cannot the equations of radiation fall into place with the same elegant inevitability? But they do not. The blackbody problem remains unsolved. Classical physics, that completed edifice he was told about at 16, has a crack running through its foundation. And the crack is widening. Autumn arrives in 1899. Leaves fall in Berlin's Tiergarten. Max walks to his university office through the morning cold. He has one more idea to try, one more mathematical approach. It will probably fail like all the others, but he is patient. He is methodical. He will keep trying until he either solves the problem or proves it unsolvable. He does not know that in 12 months he will write the equation that changes everything. He does not know that his years of failure are about to bear impossible fruit. He does not know that the classical physics everyone told him was complete is about to shatter. He knows only that he cannot stop. The problem has taken hold of him, and Max Planck, who chose physics for its certainty and order, is about to discover that at the deepest level, the universe is neither certain nor orderly in the way anyone imagined. The seeds of revolution have been planted, in a quiet Berlin study, in the mind of a methodical thermodynamicist, in the gap between what physics predicts and what nature does. Now they wait to sprout, and when they do, nothing will ever be the same. October 1900 arrives in Berlin with crisp autumn air and lengthening shadows. Max Planck sits in his study surrounded by 5 years of failed calculations. Papers cover his desk, his shelves cascade onto the floor. Each sheet represents another approach that led nowhere, another promising path that ended in contradiction. He is 52 years old. His hair is greying. His children are growing into their own lives. Carl, now 13, shows his father's aptitude for mathematics. The twins, Grete and Emma, are 11. Young Erwin is 7 and little Marie just 5. They fill the household with noise and life, a welcome distraction from the equations that refuse to cooperate. But Max cannot escape the problem. It haunts him. Every heated object in his life, every lamp, every stove, every ray of sunlight streaming through his window is a reminder. These things emit radiation according to laws that physics cannot explain. In early October, desperation leads him to try something radical. Not because he believes it will work, but because he has exhausted every reasonable option. What remains must be unreasonable. What if energy is not continuous? What if it comes in packets, discrete units, indivisible chunks? The idea violates everything physics has established. Energy flows smoothly. You can have any amount of energy whatsoever. There is no minimum quantity, no smallest possible unit. To suggest otherwise is to reject 2 centuries of successful classical physics. But Max makes the assumption anyway, just temporarily, he tells himself, just as a mathematical convenience. He will divide energy into finite elements, use them to make the calculation tractable, and then let them shrink to 0 at the end. A trick, nothing more. He works through the mathematics. The calculation is complex, involving statistical mechanics and thermodynamics, probability distributions, and energy states. For days, he manipulates the equations, checking and rechecking each step. And then something extraordinary happens. The formula works. It matches the experimental data perfectly. At all wavelengths, at all temperatures, the ultraviolet catastrophe vanishes as if it never existed, but only if the energy packets do not shrink to 0, only if they remain finite, only if energy truly is quantized into discrete units. Max stares at his result. He checks the mathematics again, searching for an error. There is none. The equation is correct, but it requires accepting something impossible. On October 19th, 1900, Max presents his formula to the German Physical Society. He stands before his colleagues and writes the equation on the blackboard. It describes precisely how much energy a black body emits at each wavelength as a function of temperature. The physicists in attendance recognize immediately that it works. The fit with experimental measurements is perfect. After years of trying, someone has finally solved the blackbody problem. But Max does not explain about the quanta, not yet. He has found a formula that works, but he does not understand why it works. He needs time to think, to explore, to see if he can derive this result from deeper principles. For the next 2 months, Max works with an intensity he has never before experienced. He barely sleeps. He neglects his teaching duties. He is consumed by a single question. What does this formula mean? He explores every possible interpretation. Perhaps the quantization applies only to the oscillators in the cavity walls, not to the radiation itself. Perhaps there is some constraint on energy exchange that classical physics missed. Perhaps the mathematics is telling him something about the statistical nature of thermodynamics rather than about energy itself. But every approach leads to the same conclusion. If the formula is correct, and the experimental evidence says it is, then energy must be quantized, not just in heated cavities but everywhere, not just for certain systems but for all electromagnetic radiation. Energy comes in packets, quanta, discrete, indivisible units, whose size depends on frequency. December 14th, 1900. The date will be remembered as the birthday of quantum mechanics, though no one present that day understands its significance. Max stands before the German Physical Society once more. His hands tremble. He is about to announce something that contradicts everything he has believed, everything he has taught, everything physics has established since Newton. He explains his derivation. Energy, he says, cannot have arbitrary values. For electromagnetic radiation of a given frequency, there is a minimum energy unit. The energy must be an integer, multiple of this fundamental quantum. He writes the equation on the blackboard. E equals h times frequency. That constant h is a new fundamental constant of nature. Max has calculated its value from experimental data. 6.626 times 10 to the minus 34th joule seconds. Imagine how small this number is. Take a second and divide it into 10 trillion parts. Then divide each of those parts by another 6. That is, approximately Planck's constant, an inconceivably tiny quantity, so small that in everyday life, the quantization of energy is completely undetectable. Energy appears continuous because the individual packets are far too small to notice. But at the atomic scale, where the energies involved are themselves tiny, this graininess becomes crucial. A single quantum of violet light carries about 4 times 10 to the minus 19th joules. That is 2.5 times Planck's constant, multiplied by the frequency of violet light. At this scale, you cannot have half a quantum or 1.5 quanta. You have 0 quanta, 1 quantum, 2 quanta, discrete, countable units. The scientists in the audience listen. Some grasp the mathematics. Others simply appreciate that Planck has solved a problem that defeated everyone else. But few understand what he has really done. The implications are too radical, too far removed from established physics. And Max himself hopes he is wrong. For months afterward, he searches desperately for an error. He tries to derive the blackbody formula without quantizing energy. He explores whether the quanta might be just a mathematical artifact, a convenient fiction that simplifies calculation but does not reflect physical reality. He fails. Every approach that preserves continuous energy leads back to the ultraviolet catastrophe. Every successful derivation requires quantization. Nature, it seems, has made a choice. And that choice is fundamentally different from what anyone expected. Consider what this means. You cannot add arbitrary amounts of energy to a system. You cannot have any energy value you want. Energy comes in specific, discrete packets. The universe has a fundamental graininess, a resolution below which it will not operate smoothly. This is not just strange, it is philosophically revolutionary. Since Newton, physics had been built on calculus, on the mathematics of continuous change, on infinitesimal differences. The assumption was that you could always divide things more finely, could always consider smaller and smaller intervals. There was no limit to resolution. But Planck's constant says otherwise. There is a limit. Below a certain scale of action, defined by h, nature refuses to be continuous. The universe is fundamentally discrete. At home, Max plays his piano with new intensity. The music is continuous, each note flowing into the next, vibrations in the air smoothly transitioning through frequencies. But now he knows that underneath this apparent continuity, something else is happening. Each sound wave is carried by quantized energy exchanges, by discrete packets of vibration. The smoothness is an illusion created by unfathomable numbers of tiny, discrete events. His children notice his distraction. Papa seems troubled, they tell their mother. Marie understands. She has lived with him through 5 years of this problem. She knows what it means to him, how deeply he cares about understanding nature's laws. Now he has found something, and it frightens him, because Max Planck is a conservative by nature. He believes in order, in classical values, in the edifice of established knowledge. He did not set out to revolutionize physics. He wanted only to solve a technical problem within the existing framework. But the problem would not be solved that way. It demanded revolution. 5 years pass. Max continues his work, exploring the implications of quantization, trying to understand this strange new constant he has introduced. He publishes papers, gives lectures, corresponds with other physicists. But he is careful, cautious, unwilling to push the quantum idea too far. Then, in 1905, a young patent clerk in Bern named Albert Einstein reads Planck's paper. Einstein is 26 years old, unknown in the physics community, working full-time examining patent applications while pursuing physics in his spare time. Einstein is thinking about the photoelectric effect. When light strikes certain metals, it ejects electrons. But the phenomenon has strange properties that classical wave theory cannot explain. The energy of the ejected electrons depends on the light's frequency, not its intensity. Shine brighter light, and you get more electrons but not more energetic ones. Only increase the frequency, and the individual electrons gain more energy. This makes no sense if light is purely a wave. A wave's energy depends on its amplitude, its brightness, not its frequency. But Einstein sees something. What if Planck's energy quanta apply not just to matter but to light itself? What if electromagnetic radiation does not just interact with matter in discrete packets, but actually is made of discrete packets? Light quanta. Individual particles of light, each carrying energy equal to Planck's constant times frequency. Later, these will be called photons. But in 1905, Einstein simply proposes that light has a particle nature, in addition to its wave nature. The photoelectric effect makes perfect sense with light quanta. Each quantum strikes an electron and transfers all its energy at once. Higher frequency quanta carry more energy, so they eject electrons with more kinetic energy. Brighter light contains more quanta, so more electrons are ejected, but the individual electron energies remain the same. Einstein publishes his paper on the photoelectric effect in March 1905. It is one of 4 groundbreaking papers he publishes that year, his miracle year. The others explain Brownian motion, establish special relativity, and derive E equals mc squared. Any one of these papers would make a career. Einstein produces all 4 while working as a patent clerk. When Max reads Einstein's paper, he is horrified. This is too much. Max had quantized the energy exchange between matter and radiation, hoping it was just a property of how atoms absorb and emit light. But Einstein is quantizing light itself. He is saying that the electromagnetic wave, the beautiful continuous wave Maxwell had unified with optics, is actually a stream of particles. This contradicts everything. Light creates interference patterns, proving it is a wave. Light diffracts around obstacles, refracts through lenses, polarizes, all wave phenomena. How can it also be particles? Yet Einstein's explanation of the photoelectric effect is compelling, and when experimentalists test the predictions, they work perfectly. The energy of ejected electrons increases linearly with frequency, exactly as Einstein predicted, with Planck's constant as the proportionality factor. Max tries to resist. He calls Einstein's light quanta too radical, an unnecessary complication, but the evidence accumulates. By 1913, Robert Millikan, trying to disprove Einstein's photoelectric equation, instead confirms it with high precision. Millikan even gets an accurate measurement of Planck's constant from the data. The quantum is spreading. It is no longer just Planck's strange solution to one problem. It is becoming a general principle. And physicists are beginning to realize that if energy is quantized, then many mysteries suddenly make sense. In 1913, a young Danish physicist named Niels Bohr proposes a model of the hydrogen atom. Electrons orbit the nucleus, Bohr says, but not in arbitrary orbits. Only certain discrete orbits are allowed, orbits whose angular momentum is an integer multiple of Planck's constant divided by 2 pi. Why don't atoms collapse, with electrons spiraling into the nucleus as they radiate energy? Because, Bohr says, there is a lowest allowed orbit. Below that, there are no permitted energy states. The electron cannot fall further because there is nowhere quantum mechanically allowed for it to fall to, and when electrons jump between these discrete orbits, they emit or absorb photons whose energy equals the energy difference between levels. This explains why atoms emit light at specific wavelengths, why hydrogen has its characteristic spectral lines. Each line corresponds to a transition between quantum energy levels. Bohr's model works beautifully for hydrogen, It predicts the spectral lines with remarkable accuracy, and it does so using Planck's constant, that number Max calculated in desperation in 1900. The constant is everywhere. It appears in every calculation involving atomic structure, every formula for electromagnetic radiation, every equation dealing with energy at small scales. It has become as fundamental to physics as the speed of light or the gravitational constant, and Max Planck, the reluctant revolutionary, must watch as his discovery takes on a life of its own. Young physicists embrace the quantum idea with enthusiasm he cannot share. They push it further than he ever intended, into territories that make him deeply uncomfortable. But there is no going back. The quantum is real. Planck's constant is a fundamental property of nature. The universe operates at the smallest scales, not through continuous flows, but through discrete jumps. Max will spend the rest of his life trying to understand what he discovered, trying to reconcile quantum mechanics with his belief in an ordered, deterministic universe, trying to find meaning in the fact that nature, at its deepest level, is granular rather than smooth. He succeeded in solving the blackbody problem, but the solution opened questions far deeper and stranger than the original puzzle. He found an answer that became a question, a constant that revealed inconstancy at the heart of classical physics, a number so small it is negligible in daily life, yet so important it governs every interaction between light and matter. December 14th, 1900. The day Max Planck stood before his colleagues with trembling hands and announced the quantum. The day physics changed forever, the birthday of a new understanding of reality, and the beginning of a revolution that would consume the next century of science. The quantum idea spreads through European physics like wildfire through a dry forest. What Planck discovered reluctantly, what Einstein seized upon boldly, now becomes the obsession of a generation of young physicists who see that classical physics cannot explain the atomic world. By 1913, atoms are no longer philosophical abstractions. They are real, measurable, and deeply mysterious. Ernest Rutherford has shown that atoms have tiny, dense nuclei. Electrons orbit these nuclei somehow. But how? Classical physics predicts they should spiral inward in a fraction of a second, radiating away their energy. Yet atoms are stable. Matter endures. Niels Bohr solves this with quantum mechanics. Electrons occupy discrete energy levels, he proposes. They cannot spiral gradually inward because there are no intermediate energies available. They must jump instantaneously between allowed states, emitting or absorbing photons as they go. This quantum jump becomes physics's most revolutionary concept. Not smooth transitions, but discontinuous leaps. An electron here, then there, with no path between. It simply jumps, and in jumping, creates or destroys a photon. The idea is absurd by classical standards. How can something move without traversing the space between? Yet it works. Bohr's model predicts hydrogen spectral lines with stunning accuracy, and it does so using Planck's constant as the fundamental scale that determines which orbits are allowed. Then comes the Great War. In August 1914, Europe descends into mechanized slaughter. Germany mobilizes, Austria-Hungary mobilizes, Russia mobilizes, France, Britain, the Ottoman Empire. Within weeks, millions of men are marching toward trenches that will devour them. Max Planck, like many German intellectuals, initially supports his country. This is a war for German culture, German civilization, he tells himself. But as the casualties mount, as the initial enthusiasm curdles into horror, his patriotism turns to despair. His son Karl is called up. The boy who showed such promise in mathematics, who might have followed his father into physics, becomes a soldier. In 1916, Karl is sent to Verdun, where French and German armies are locked in the war's bloodiest battle. For 10 months, they pound each other with artillery. 300,000 men die. Karl Planck is one of them. A letter arrives in Berlin. Brief, formal. The army regrets to inform the family. Max reads it, and something breaks inside him. All his understanding of nature's laws, all his knowledge of how the universe works at the deepest level, is useless against this. He cannot calculate away grief. There is no equation for loss. But the war continues. The quantum revolution continues. Even as civilization tears itself apart, young physicists keep thinking about atoms and radiation and the strange new rules that govern the microscopic world. In 1916, Einstein publishes his theory of stimulated emission. An atom in an excited state, Einstein shows, can be triggered to emit a photon by the presence of another photon of the same energy. This will eventually lead to lasers, though Einstein does not know it. He is simply following the quantum logic wherever it leads. Arnold Sommerfeld extends Bohr's model to elliptical orbits. The atom becomes more complex, more detailed. Each electron has not just an energy level but angular momentum, magnetic properties. The quantum numbers multiply. The picture grows richer and stranger. Then, in 1917, tragedy strikes the Planck household again. Grete, now 28, dies in childbirth. She had married and was bringing a new life into the world. But complications arise, and both the delivery and modern medicine fail. Max loses another child. 2 years later, 1919, Emma dies the same way. The twin daughters, inseparable in life, united in the manner of their deaths, both in their 20s, both trying to start families of their own, both gone. Max Planck has now buried 3 of his 5 children. His first wife Marie died in 1909. He has remarried, seeking companionship in his grief, but the losses accumulate like snow, each one making the burden heavier. And still, the quantum revolution accelerates. The war ends in November 1918. Germany is defeated, humiliated, economically ruined. The Kaiser abdicates. The Weimar Republic is born into chaos, but physics continues. In 1918, Max Planck receives the Nobel Prize for his discovery of energy quanta. The award recognizes work he did 18 years earlier, work he has spent those 18 years trying to undo or at least limit. But the Nobel Committee sees clearly what Max himself struggled to accept. He changed physics forever. The 1920s bring the quantum revolution to its climax. A new generation of physicists born around 1900 comes of age. They have no attachment to classical physics, no nostalgia for the old certainties. They embrace the quantum world with enthusiasm and audacity. In 1923, Louis de Broglie proposes that if light can be both wave and particle, perhaps matter can too. Perhaps electrons are not just particles but also waves. The idea seems mad, but experiments soon confirm it. Electrons create diffraction patterns just like light does. Everything is both particle and wave. Then, in the summer of 1925, breakthrough arrives from an unexpected place. Werner Heisenberg, only 23 years old, is suffering from hay fever. To escape the pollen, he travels to Helgoland, a tiny island in the North Sea. There, alone, recovering, Heisenberg has an insight. He realizes that physicists have been thinking about atomic orbits wrong. You cannot observe an electron's position and momentum simultaneously with arbitrary precision. The act of measurement disturbs what you measure. So why base your theory on unobservable quantities like electron orbits? Instead, base it on what you can actually observe. The light atoms emit, the energies of transitions. Working through this logic, Heisenberg develops matrix mechanics. It is a new mathematical framework for quantum mechanics, based on matrices rather than ordinary numbers. The mathematics is strange, unfamiliar to most physicists, but it works. It predicts atomic spectra correctly, without assuming classical orbits at all. The following year, 1926, Erwin Schrödinger, working in Zurich, develops a different approach. Schrödinger creates wave mechanics, treating electrons as waves described by a wave function. His equation, the Schrödinger equation, becomes the fundamental equation of quantum mechanics. Remarkably, Schrödinger's wave mechanics and Heisenberg's matrix mechanics turn out to be mathematically equivalent. Two completely different approaches, two different mathematical languages, describing the same quantum reality. But what is that reality? The wave function gives probabilities, not certainties. Before you measure an electron's position, it does not have a definite position. It exists in a superposition of many possible positions. Only when you measure does the wave function collapse to a definite state. This probabilistic interpretation troubles many physicists, Einstein especially. He cannot accept that God plays dice with the universe. There must be deeper variables, he argues, hidden mechanisms that determine outcomes. The quantum mechanics everyone is developing must be incomplete. In October 1927, the fifth Solvay conference convenes in Brussels. The topic is electrons and photons. The greatest physicists in the world gather to debate the meaning of quantum mechanics. Einstein and Bohr engage in legendary discussions. Einstein proposes thought experiment after thought experiment, trying to show that quantum mechanics leads to contradictions or allows you to violate the uncertainty principle. Each morning he arrives with a new challenge. Each time Bohr thinks through the problem and shows why Einstein's objection fails. Max Planck attends this conference. He is 69 years old now, the elder statesman of quantum physics. He watches Einstein and Bohr battle over the theory that emerged from his 1900 discovery. He listens as young Heisenberg explains the uncertainty principle. You cannot know both position and momentum with arbitrary precision. He hears Bohr articulate the Copenhagen interpretation. Quantum mechanics is complete, probability is fundamental. Asking what happens between measurements is meaningless. These young physicists are taking his quantum much further than he ever imagined. They are building a picture of reality that is fundamentally indeterministic, fundamentally uncertain. And they are doing it with brilliant confidence, sure that they are right. Max is less sure. He has never fully embraced the quantum revolution he started. He still hopes for a return to classical determinism, for an understanding that preserves continuity and certainty. But the evidence keeps supporting the quantum interpretation. Experiment after experiment confirms the predictions of this strange new mechanics. Meanwhile, Germany is struggling. The Weimar Republic faces economic chaos, political extremism, social upheaval. The humiliation of Versailles festers. In Munich, a failed artist named Adolf Hitler is building a movement based on resentment and racial hatred. Max, now in his 70s, holds enormous prestige in German science. He is president of the Kaiser Wilhelm Society, Germany's premier scientific organization. He uses his influence to support younger physicists, to maintain funding for research, to preserve what he can of German scientific institutions. He also begins to speak out against the Nazi Party's growing anti-Semitism. Many of Germany's greatest physicists are Jewish. Einstein, Born, Franck, Haber. To attack them is to attack German science itself. Max argues this forcefully, using his reputation to shield Jewish colleagues from harassment. It is not enough. The Nazis grow stronger. They brand modern physics as Jewish physics, a Jewish conspiracy to corrupt German thought. Relativity and quantum mechanics are declared un-German. The Nazis want a pure Aryan physics based on intuition rather than abstract mathematics. This is insanity. Max thinks. Physics has no nationality, no race. Truth is truth regardless of who discovers it. But the Nazi rhetoric resonates with parts of German society desperate for simple answers, for scapegoats, for a return to imagined past glory. In 1933, Hitler becomes Chancellor. Within months, Jewish professors are dismissed from universities. Einstein flees to America. Max von Laue, one of Max Planck's closest friends, risks his career defending Jewish colleagues. Max himself does what he can, but his influence is fading. The regime does not care about scientific prestige. Max watches Germany destroy itself. The country that produced Gauss and Riemann, Helmholtz and Hertz, Kirchhoff and Clausius and himself, is driving away its greatest scientific minds, all in service of a racist ideology that contradicts everything science stands for. His son Erwin, now working in the civil service, shares his father's horror at what Germany is becoming. Erwin is no revolutionary. He is a quiet man, a civil servant, someone who believes in duty and proper procedure. But he cannot stomach the Nazis. He cannot participate in this madness. As the 1930s progress, Erwin becomes involved with people who oppose the regime. Not active resistance, not plots or sabotage, just conversations, just the maintenance of human decency in an indecent time. Just the simple act of saying, no, this is wrong. Meanwhile, the quantum mechanics Max reluctantly birthed matures into a complete theory. Physicists develop quantum electrodynamics, explaining how light and matter interact. They begin to understand nuclear physics, how protons and neutrons bind into atomic nuclei. They predict new particles, new phenomena, and every equation, every calculation, every prediction uses Planck's constant. That number Max, computed in desperation in 1900, has become woven into the fabric of modern physics. You cannot do quantum mechanics without it. Max is now in his 80s. He has seen his discovery transform physics. He has seen 3 of his children die. He has seen Germany rise to scientific dominance and then tear itself apart. He has outlived his first wife, outlived the German Empire, outlived the brief hope of Weimar democracy, and the worst is still to come. The war his son Karl died in was not, as everyone hoped, the war to end all wars. It was merely the first act. In September 1939, Germany invades Poland. The Second World War begins. Max Planck, 81 years old, watches his country plunge into another catastrophic war. This one will be worse, more mechanized, more total, more murderous. This one will consume not millions but tens of millions. This one will reveal depths of human evil that even the pessimist Clausius, with his increasing entropy, might not have imagined. And this one will take Max's last son. The Gestapo is watching Erwin. They know about his associates, his quiet opposition, his refusal to embrace the regime. They are waiting for an excuse. The quantum revolution continues. Even in wartime, even as bombs fall and cities burn, physicists keep working. Some flee to allied countries and begin developing the atomic bomb. Others remain in Germany, working on their own nuclear research. Science has no allegiance to morality. It reveals how nature works. How humans use that knowledge is another matter entirely. Max Planck discovered how to manipulate energy at the quantum level. Now that knowledge is being weaponized. The constant he calculated will appear in the equations governing nuclear fission, governing the chain reactions that will destroy Hiroshima and Nagasaki. His discovery, born from the abstract problem of blackbody radiation, will become a tool for ending the war and beginning the atomic age. But in 1945, as the war reaches its terrible climax, Max's personal world collapses once more. The Gestapo arrests Erwin Planck, and this time no amount of scientific prestige can save him. Stand in your home and look around. The light from your LED bulbs, the phone in your pocket, the computer on your desk, the solar panels on roofs across your neighborhood. Every one of these devices operates through principles that Max Planck discovered while trying to solve an obscure problem about heated cavities. His constant, that impossibly tiny number he calculated in desperation in 1900, now appears in the equations, governing billions of transistors switching on and off billions of times per second in the device you are likely holding right now. Consider your smartphone. Inside it are approximately 10 billion transistors, each one smaller than a virus. These transistors work through quantum tunneling, a phenomenon that exists only because energy is quantized. An electron faces a barrier it classically cannot cross, but in quantum mechanics, the electron has a probability of tunneling through the barrier, of appearing on the other side without ever having the energy to climb over. This would be impossible in classical physics. But at quantum scales, governed by Planck's constant, the impossible becomes routine. Each transistor uses this tunneling effect to switch between on and off states, binary, 0 or 1. The foundation of all digital computation, 10 billion quantum switches in a device that fits in your palm, each one operating according to the principles Max Planck reluctantly discovered, each one proving, trillions of times per second, that energy is quantized, that reality at small scales is fundamentally different from our everyday experience. The screen you are looking at emits light through quantum mechanics. LEDs, light-emitting diodes, work because electrons in semiconductor materials occupy discrete energy levels. When an electron drops from a higher level to a lower one, it emits a photon whose energy equals the energy difference. The color of that photon, its frequency, is determined by Planck's equation. E equals h times frequency. Engineers design LEDs by choosing materials with specific energy level spacings. Want red light? Use a semiconductor with a smaller energy gap. Want blue light? Use one with a larger gap. The precision of modern LEDs, their efficiency and brightness, comes from our quantum mechanical understanding of how electrons behave in crystalline solids. This understanding traces directly back to Planck's constant. Without it, without the quantization of energy, there would be no way to predict which materials emit which colors, no way to design the light sources that have replaced incandescent bulbs across the world. Look outside. If you see solar panels, you are seeing quantum mechanics harvesting energy from sunlight. The photoelectric effect that Einstein explained using Planck's light quanta is the fundamental principle behind every solar cell. A photon strikes a semiconductor. If its energy exceeds a threshold determined by the material's quantum properties, it liberates an electron. That electron flows through a circuit. Sunlight becomes electricity through a purely quantum mechanical process. The efficiency of solar panels has increased dramatically over decades because physicists and engineers understand the quantum mechanics involved. They know how to design materials that absorb photons efficiently, that minimize energy loss, that convert solar radiation into electrical current with ever-improving yields. Planck's constant appears in every calculation. In hospitals, MRI scanners read the quantum spin of hydrogen atoms in your body's water molecules. Spin is a purely quantum mechanical property with no classical analog. Hydrogen nuclei act like tiny magnets that can point up or down relative to a magnetic field. When radio waves of the right frequency hit these nuclei, they flip their spin, absorbing energy equal to, you guessed it, Planck's constant times the radio frequency. Different tissues in your body contain different densities of hydrogen. Fat, muscle, blood, tumors. Each produces a different signal strength. The MRI scanner builds a three-dimensional map of your internal structures by detecting these quantum spin flips. It can find tumors smaller than a grain of rice, can spot blood clots in vessels narrower than a hair, all through quantum mechanics. Consider GPS. The satellites orbiting Earth at 20,000 kilometers keep time with atomic clocks accurate to nanoseconds. These clocks work by counting oscillations of cesium atoms as electrons jump between quantum energy levels. The frequency of these jumps, defined by the energy difference divided by Planck's constant, provides a time standard so precise that errors of less than 1 second accumulate over 300,000 years. But even these incredible clocks require quantum mechanical corrections. Einstein's relativity predicts that time runs differently in different gravitational fields and at different speeds. The GPS satellites experience both effects. They are moving fast relative to Earth's surface, which slows their clocks through special relativity. But they are also in weaker gravity, which speeds their clocks through general relativity. The net effect is that satellite clocks run about 38 microseconds faster per day than ground clocks. Without correcting for this relativistic time dilation, GPS would accumulate errors of 10 kilometers per day. Your navigation would be useless. The system works only because engineers account for both quantum mechanics in the atomic clocks and relativity in the time corrections. Planck's constant and Einstein's theories, working together to keep you from getting lost. In surgery, doctors use lasers that exist only because of quantum mechanics. Laser stands for light amplification by stimulated emission of radiation. The stimulated emission Einstein predicted in 1916, where one photon triggers an atom to emit another identical photon. Chain reactions of photon emission, all in phase, all the same frequency, all traveling in the same direction. Coherent light of extraordinary intensity and precision. Surgeons use lasers to cut tissue, seal blood vessels, reshape corneas, to remove tumors. The precision is possible because laser light is so highly controlled. Its wavelength is determined by the quantum energy levels in the laser medium. Its coherence comes from the quantum mechanical process of stimulated emission. Planck's constant governs every aspect. The global economy depends on semiconductor manufacturing. Computer chips, memory modules, processors, sensors, all rely on quantum mechanics. The feature sizes on modern chips are measured in nanometers, distances so small that quantum effects dominate. Electrons tunnel through barriers. Their wave nature determines how they flow through channels. Quantum interference patterns affect device performance. Engineers designing these chips use quantum mechanics constantly. They simulate electron wave functions. They calculate tunneling probabilities. They account for quantum confinement effects when structures become so small that electrons behave less like particles and more like waves in a box. Every design tool, every simulation, every calculation uses Planck's constant. Without quantum mechanics, the digital revolution could not have happened. There would be no transistors, no integrated circuits, no computers, no internet. The modern world is built on quantum foundations, but the quantum revolution extends beyond electronics. In chemistry, quantum mechanics explains why atoms form molecules, why some materials are hard and others soft, why carbon can be diamond or graphite or graphene depending on how its atoms arrange themselves. Chemical bonds exist because electrons occupy quantum orbitals around nuclei. These orbitals have shapes and energies determined by solving Schrödinger's equation. The electron is not a particle orbiting like a planet, but a wave distributed around the nucleus in patterns of probability. Where the wave has high amplitude, you are likely to find the electron. Where it has zero amplitude, you will never find it. Chemists design new drugs by understanding these quantum orbitals. They model how molecules fit together, how electrons are shared between atoms, how energy is exchanged in chemical reactions. Pharmaceutical companies use quantum chemistry simulations to screen millions of potential drug candidates, looking for ones that will bind to disease proteins with high specificity. In materials science, Quantum mechanics explains superconductivity. Certain materials, when cooled below a critical temperature, lose all electrical resistance. Current flows through them forever without any energy loss. This happens because electrons pair up through a quantum mechanical effect, forming what is called a Cooper pair. These pairs move through the material without scattering off atoms, without losing energy. Superconducting magnets use this property. The Large Hadron Collider, near Geneva, uses superconducting magnets to bend particle beams around its 27-kilometer ring. MRI machines use superconducting magnets to generate their powerful fields. Maglev trains levitate above tracks using superconducting magnets, all exploiting a purely quantum phenomenon. Scientists are now building quantum computers. These devices use quantum bits, or qubits, that can exist in superposition states. A classical bit is either 0 or 1. A qubit can be 0, 1, or both simultaneously. This superposition allows quantum computers to perform certain calculations exponentially faster than classical computers. Google achieved quantum supremacy in 2019, performing a calculation in minutes that would take the world's fastest classical supercomputer thousands of years. IBM, Microsoft, and dozens of startups are racing to build larger, more stable quantum computers. These machines exploit the same quantum principles Planck discovered: superposition, entanglement, quantized energy levels. The applications are staggering. Quantum computers could crack every encryption system currently protecting internet commerce and communications. They could simulate molecular interactions with perfect accuracy, revolutionizing drug discovery. They could optimize logistics networks, financial portfolios, traffic flows with unprecedented efficiency. They could solve problems in artificial intelligence that are currently intractable. But building quantum computers is extraordinarily difficult. Qubits are fragile. Any interaction with the environment causes decoherence, destroying the quantum superposition. Quantum computers must operate at temperatures near absolute zero, in isolated chambers, with error correction schemes that require hundreds of physical qubits to create one stable logical qubit. Yet progress continues. Each year, quantum computers get larger and more reliable. Researchers develop new qubit technologies, superconducting circuits, trapped ions, photons, topological states, all of them based on quantum mechanics, all of them governed by Planck's constant. Beyond computing, scientists are discovering that quantum effects appear in biology. Photosynthesis, the process by which plants convert sunlight into chemical energy, achieves 95% efficiency. This remarkable efficiency comes from quantum coherence. Energy absorbed by light-harvesting molecules is transferred to reaction centers along multiple paths simultaneously through quantum superposition. The system finds the most efficient route by exploring all routes at once. European robins navigate using Earth's magnetic field. But how do they sense such a weak field? Researchers discovered that certain proteins in the bird's eyes contain pairs of electrons that become quantum entangled when struck by blue light. The entangled pairs respond to magnetic fields, providing the birds with a quantum compass. They literally see magnetic field lines through quantum entanglement. Even consciousness might have quantum origins. Roger Penrose and Stuart Hameroff proposed that quantum processes in brain microtubules, tiny structures inside neurons, could explain aspects of consciousness that seem difficult to account for with classical physics. The hypothesis is controversial, but it suggests that quantum mechanics might be relevant even to the emergence of subjective experience. Whether or not consciousness is quantum, the human brain certainly uses quantum mechanics in its chemistry. Every neural signal involves ions flowing through channels in cell membranes. These channels open and close through conformational changes in proteins, changes governed by quantum mechanical interactions between atoms. Neurotransmitters bind to receptors through quantum orbital overlaps. The brain operates on electrochemical principles that are fundamentally quantum at the atomic level. Look up at night, far from city lights. The stars you see shine through quantum fusion. In the sun's core, hydrogen nuclei overcome their electromagnetic repulsion through quantum tunneling, fusing into helium and releasing energy according to E=mc². Without quantum tunneling, the sun would not shine. Without fusion, there would be no sunlight, no photosynthesis, no life on Earth. Every atom in your body heavier than hydrogen was forged in stellar interiors through quantum processes. Carbon, nitrogen, oxygen, calcium, iron, all created by fusion reactions in stars that exploded billions of years ago. You are made of quantum mechanics. Your existence depends on processes governed by Planck's constant. The air you breathe consists of molecules held together by quantum chemical bonds. The ground beneath your feet is solid because of quantum mechanical effects that determine how atoms pack together. The colors you see exist because electrons in atoms absorb and emit photons at frequencies determined by quantum energy levels. Max Planck, trying to solve the blackbody radiation problem in 1899, could not have imagined any of this. He was thinking about heated cavities and electromagnetic theory. He was not imagining smartphones or solar panels or MRI scanners or quantum computers. He was certainly not thinking about quantum effects in bird navigation or photosynthesis. Yet his discovery underlies all of it. The constant he calculated, that impossibly tiny number, turned out to be one of nature's fundamental constants, as important as the speed of light, as universal as the gravitational constant, a number that appears in every equation describing the atomic and subatomic world. Civilization now runs on quantum mechanics. The technologies that define modern life, the devices you use every day, the medical treatments that extend lifespans, the communications networks that connect the world, all operate through principles discovered in the quantum revolution that Planck reluctantly started. We live in a quantum civilization, and we have only begun to exploit these principles. The next century will likely see even more dramatic applications: room temperature superconductors that transmit electricity without loss, quantum sensors that detect dark matter or gravitational waves, quantum communication networks that are perfectly secure against eavesdropping, technologies we cannot yet imagine based on quantum phenomena we are only beginning to understand. But all of it traces back to December 14th, 1900, to Max Planck standing before the German Physical Society with trembling hands, announcing that energy comes in discrete packets, to one man's desperate solution to an obscure problem in thermodynamics. The quantum is everywhere, in your pocket, in your walls, in your body, in the stars. It is the foundation of modern physics, the basis of modern technology, the framework through which we understand reality at its deepest level. And it began with an act of desperation by a grieving physicist who outlived 4 of his 5 children but gave humanity the key to understanding and manipulating matter at the smallest scales. Max Planck's personal darkness bred light. The light in your screen, the light in surgical lasers, the light of understanding itself. Quantum civilization born from one man's refusal to surrender to an impossible problem. The quantum revolution is not finished. In laboratories across the world, scientists push toward discoveries that will reshape civilization as profoundly as transistors and lasers did in the 20th century. The next decades will reveal whether we can truly master the quantum realm, or whether its deepest mysteries will forever resist human understanding. Consider what is coming. What must come if current research continues its trajectory? Quantum computers with 1 million qubits will arrive within our lifetimes, perhaps sooner than we expect. Today's quantum computers have fewer than 1,000 qubits and require elaborate error correction. But progress is exponential. Each breakthrough enables the next. Each solved problem reveals 10 new ones, but also 10 new solutions. A 1,000,000-qubit quantum computer will crack every encryption system currently protecting internet commerce. RSA encryption, the foundation of secure communication, depends on the difficulty of factoring large numbers into primes. Classical computers need thousands of years to factor a number with hundreds of digits. A sufficiently large quantum computer could do it in hours, using Shor's algorithm. Adversaries are already harvesting encrypted data, storing it, waiting for the quantum computers that will unlock it. Medical records, financial transactions, government communications, corporate secrets, all encrypted today with methods that will become transparent tomorrow. The solution is quantum-proof cryptography, post-quantum algorithms based on mathematical problems that even quantum computers cannot efficiently solve. Lattice-based encryption, hash-based signatures, code-based cryptography. Governments and technology companies are racing to deploy these systems before quantum computers make current. Encryption obsolete. But here is the deeper revolution. Quantum key distribution uses the principles of quantum mechanics itself to create perfectly secure communication. Send quantum states, individual photons in superposition, from one location to another. Any attempt to intercept or measure these photons inevitably disturbs them through the act of measurement. The recipient knows immediately if anyone has eavesdropped. This is not encryption that is merely difficult to crack. It is communication whose security is guaranteed by the laws of physics themselves, by the uncertainty principle, by the fact that measurement collapses quantum superposition. Hack this, and you have disproven quantum mechanics itself. China has already launched a quantum communication satellite. Ground stations in Beijing and Vienna have exchanged quantum encrypted messages through space. The technology is maturing from laboratory demonstration to practical deployment. Within decades, quantum communication networks may protect the most sensitive information on Earth. But quantum computers promise far more than code breaking. They will revolutionize drug discovery. Simulating how molecules interact requires calculating quantum mechanical wave functions for every electron involved. The complexity grows exponentially with the number of particles. Classical computers struggle to simulate even simple molecules accurately. Quantum computers are natural molecular simulators. They are quantum systems simulating other quantum systems. A quantum computer with sufficient qubits could model protein folding, predict how drug candidates bind to disease targets, and design new materials with specified properties, all with quantum precision. Imagine designing a drug by specifying exactly what you want it to do, then having a quantum computer search through billions of possible molecular structures to find candidates that will work. Testing happens in simulation before synthesis. Failures are identified, computationally rather than experimentally. The cost and time required for drug development could decrease by orders of magnitude. Cancer treatments, genetic diseases, antibiotic-resistant bacteria, Alzheimer's, Parkinson's, conditions that currently resist treatment might yield to drugs designed with quantum precision. We are barely beginning to understand what becomes possible when we can simulate chemistry with perfect accuracy. Room temperature superconductors will transform energy transmission. Currently, superconductors work only at temperatures near absolute zero. Maintaining these temperatures requires expensive cryogenic systems. But if materials could superconduct at room temperature, everything changes. Transmit electricity across continents without loss. No resistance means no heating, no energy dissipation. Solar power generated in deserts could flow to cities thousands of kilometers away with perfect efficiency. Wind farms in remote locations could supply urban centers without losing half the power to transmission losses. Room temperature superconductors would enable maglev trains to operate without expensive cooling systems. Powerful magnets for fusion reactors could run continuously without refrigeration. The global energy infrastructure would be fundamentally transformed. Physicists debate whether room temperature superconductivity is possible. Some materials show hints of high-temperature superconductivity under extreme pressure. Others exhibit unusual electronic properties that might, with the right modifications, lead to superconductivity at accessible temperatures. The search continues, guided by quantum mechanical theories of electron pairing and crystal structure. If we find it, if we discover materials that superconduct at room temperature, the discovery will rank among the most consequential in human history. Right alongside fire, agriculture, antibiotics, and nuclear energy, quantum sensors will detect phenomena currently beyond reach. The universe contains dark matter, 5 times more abundant than ordinary matter, holding galaxies together through gravity. Yet dark matter has never been directly detected. It does not interact with light. It passes through ordinary matter almost without effect. Almost. Dark matter particles might very rarely scatter off atomic nuclei. Quantum sensors could detect these extraordinarily faint interactions. By cooling crystals to nearly absolute zero and monitoring for the tiniest quantum excitations, physicists hope to catch dark matter in the act of colliding with normal matter. Other quantum sensors will measure gravitational waves with unprecedented precision. Einstein's general relativity predicts that accelerating masses produce ripples in spacetime itself. LIGO detected gravitational waves from colliding black holes, confirming Einstein's century-old prediction. But quantum sensors could detect far weaker signals. Binary star systems, thousands of light-years away. Remnant gravitational waves from the Big Bang itself. Quantum mechanics will reveal the universe's most subtle vibrations. Some scientists edge toward the ultimate prize: quantum gravity, a theory uniting Planck's quantum mechanics with Einstein's general relativity. These two pillars of 20th century physics remain incompatible. Quantum mechanics describes the very small. General relativity describes the very large. But at the Planck scale, where quantum effects and gravitational effects become equally important, both theories break down. The Planck length is 10 to the minus 35 meters. The Planck time is 10 to the minus 44 seconds. At these scales, space-time itself might be quantized, might come in discrete packets like energy does. The smooth geometry of Einstein's relativity might give way to a grainy, fluctuating quantum foam. String theory proposes that fundamental particles are not points but tiny vibrating strings. Loop quantum gravity suggests that space-time itself is woven from quantum loops of area and volume. Other approaches exist, each trying to reconcile quantum mechanics and gravity, each seeking the theory of everything. We do not yet know which approach is correct. We may be decades or centuries from a complete theory of quantum gravity, but Planck's constant appears in every attempt. The quantum graininess he discovered in energy seems to extend to space and time themselves. If we achieve quantum gravity, we will understand what happens inside black holes, where gravity becomes so strong that space-time curves infinitely. We will understand the first instance after the Big Bang, when the entire universe was smaller than an atom and quantum effects dominated everything. We will grasp how reality itself emerges from quantum processes. But quantum mechanics already reveals something profound about consciousness and observation. The measurement problem remains unsolved. A quantum system exists in superposition until measured. The wave function contains multiple possibilities simultaneously, but when you measure, you get one definite result. The superposition collapses. What counts as a measurement? Does it require a conscious observer, or does any interaction with a large system count? Is the collapse of the wave function a physical process, or merely our updating of knowledge about the system? Physicists disagree sharply. The Copenhagen interpretation says the question is meaningless. Quantum mechanics predicts probabilities of measurement outcomes, and that is all. Many worlds' interpretation says the wave function never collapses. Instead, every measurement splits the universe into branches containing all possible outcomes. We experience one branch, but the others are equally real. Other interpretations exist. Pilot wave theory, quantum Bayesianism, objective collapse models. Each offers a different picture of what quantum mechanics means, of what reality is at the deepest level. Max Planck would have been troubled by this. He sought universal, objective truth. Instead, his discovery led to a physics where observation affects reality, where multiple incompatible interpretations all agree on predictions but disagree on meaning. Yet perhaps this ambiguity is appropriate. Perhaps nature at the quantum level is genuinely indeterminate until actualized through interaction. Perhaps reality is not a fixed stage on which events play out, but rather emerges through the relationships between things, through the act of measurement and observation. Quantum biology continues to reveal surprising connections. Plants achieve their remarkable photosynthetic efficiency through quantum coherence. This was discovered only recently, overturning the assumption that quantum effects are too fragile to survive in warm, wet biological environments. The light harvesting complexes in plants maintain quantum superposition for hundreds of femtoseconds. That is incredibly brief by human standards, but long enough for energy to explore multiple paths simultaneously and find the most efficient route to reaction centers. Life has evolved to exploit quantum mechanics. Birds navigate using quantum entanglement in their eyes. Smell might work through quantum tunneling, with odorant molecules vibrating at frequencies that electrons in receptors can tunnel through. Enzymes might use quantum tunneling to speed up chemical reactions. Life may be deeply quantum at a level we are only beginning to appreciate. And if biology uses quantum mechanics, if evolution discovered quantum advantages millions of years before humans did, what else might be possible? Could we design quantum-enhanced biological systems? Cells that harvest light with even greater efficiency? Organisms that sense magnetic fields or gravitational waves? The intersection of quantum physics and biology remains almost entirely unexplored. Consciousness itself might involve quantum processes. The brain operates on electrochemical signals, which are classical at the level of neurons firing, but at the level of individual ion channels, of neurotransmitter molecules binding to receptors, quantum mechanics governs everything. Some researchers propose that quantum coherence in microtubules, structural proteins inside neurons, could enable non-computational aspects of consciousness. That quantum superposition might allow the brain to process information in ways that classical computation cannot replicate. That the unity of conscious experience might reflect quantum entanglement, binding separate brain regions into a coherent whole. This is speculative, controversial. Many neuroscientists dismiss it as unnecessary mysticism. But consciousness remains unexplained. We do not understand how subjective experience arises from physical processes. We do not know why there is something it is like to be conscious, rather than merely processing information without awareness. If quantum mechanics plays a role, it would mean that Planck's discovery touches not just matter and energy, but mind itself. That the constant he calculated connects to the deepest mystery of existence. Why is there experience at all? We do not know. We are still early in the quantum age. A century and a quarter after Planck presented his equation, we have built technologies he could not imagine. But we have also uncovered mysteries he could not have anticipated. Each answer reveals deeper questions. What is the quantum vacuum? Empty space, it turns out, is not empty. Virtual particles constantly pop into existence and annihilate, borrowing energy from the vacuum for impossibly brief instants allowed by the uncertainty principle. These fluctuations have measurable effects. They shift energy levels in atoms. They produce the Casimir effect, where parallel plates attract each other due to quantum vacuum pressure. The vacuum is a seething foam of quantum activity at the Planck scale, but we do not understand it. We do. We not know why the vacuum energy density is not infinite, why it does not cause the universe to collapse or expand explosively. We measure its density and find it is tiny, barely affecting cosmic expansion. But quantum mechanics predicts it should be enormous, 10 to the 120th times larger. This is the worst prediction in physics, off by 120 orders of magnitude. Something is wrong. Either quantum mechanics breaks down at cosmological scales, or our understanding of the vacuum is fundamentally flawed, or some unknown mechanism cancels the vacuum energy to incredible precision. We do not know which. These are the frontiers, the places where quantum mechanics pushes against the limits of understanding, where new discoveries wait, perhaps just beyond current experimental reach, perhaps requiring conceptual breakthroughs we have not yet imagined. The next century of quantum physics will be as revolutionary as the last. Room temperature superconductors, quantum computers with millions of qubits, quantum communication networks spanning the globe, quantum sensors detecting dark matter and gravitational waves, perhaps quantum gravity itself, perhaps quantum explanations of consciousness, or perhaps something entirely unexpected. Perhaps we will discover that quantum mechanics itself is incomplete, that there is a deeper theory waiting. Perhaps we will find that reality has more layers than we suspected, that beneath the quantum realm lies something stranger still. Max Planck stood at the beginning of this journey. In 1900, trying to solve one problem, he opened a door to an entirely new understanding of nature. Now, a century and a quarter later, we are still walking through that door, still discovering rooms beyond rooms, still finding that the quantum universe is deeper and stranger than anyone imagined. The quantum frontier stretches ahead, unlimited, unexplored, waiting for the next generation of physicists to push further, to ask new questions, to find answers that will seem as impossible to us as quantum computers would have seemed to Planck. But all of it builds on his foundation, the constant he calculated, the quantization he discovered, the revolution he started reluctantly, not knowing where it would lead. It led here, to a civilization transformed by quantum technology, to a physics that reveals reality as fundamentally uncertain, fundamentally interconnected, fundamentally strange, to a future where quantum mechanics will shape human destiny in ways we cannot yet foresee, and it will lead further still. The quantum age has only begun. We return now to where we began, to 1947, 2 years after the execution of Erwin Planck, 2 years after the war ended and Germany lay in ruins. Max Planck is 89 years old. He lives in Göttingen, a university town that survived the bombing relatively intact. The house where he stays is modest. Many of his possessions were destroyed when his Berlin home was hit during an air raid in 1944. Papers, letters, photographs. A lifetime of memories reduced to ash, but his piano survived, or rather, he found another. In the evenings, when the light fades and the day's exhaustion settles upon him, Max sits at the keyboard and plays Bach, the same pieces he played as a young student in Munich, the same music he shared with his first wife Marie and their children in happier times, the same mathematical constructions of sound that have brought him solace through decades of loss. His hands are old now, the fingers less nimble than they once were, but the music is still there. The fugues still weave their voices together with perfect logic. The preludes still explore harmonic space with architectural precision. Bach's music, like mathematics, is eternal. It was true 300 years ago when Bach composed it, and it will be true 300 years hence. Max finds comfort in this. In eternal truths. In things that remain constant even as everything else collapses. 4 of his 5 children are dead. Marie from tuberculosis, Karl at Verdun, Grete and Emma in childbirth. Erwin executed by the Nazis for opposing evil. His first wife, also named Marie, died in 1909. His second wife, Marga, survives, caring for him in these final years. Germany is divided, occupied, its cities rubble, its economy shattered, its people traumatized. The civilization Max knew, the German culture of music and philosophy and science, has been gutted by 12 years of Nazi madness and 6 years of total war. And yet, the constant he discovered remains, unaffected by war, undiminished by tragedy, unchanged by the rise and fall of empires. 6.626 times 10 to the minus 34th joule seconds. Planck's constant. A fact about reality that was true before humans existed and will remain true after humanity is gone. This is what Max grasps in his final years. Not personal immortality, not the survival of his family or his nation, but something more fundamental. He touched something eternal. He discovered a truth about the universe that transcends human affairs entirely. Every branch of physics uses his constant. Atomic physics, molecular physics, nuclear physics, particle physics, quantum field theory, quantum electrodynamics, quantum chromodynamics. The standard model of particle physics, which describes all known matter and forces except gravity, is built on quantum foundations where Planck's constant appears in every equation. The constant defines the size of atoms. It determines why matter is solid. It governs how light and matter interact. It sets the scale of uncertainty in the Heisenberg principle. It appears in the relationship between energy and frequency, between momentum and wavelength, between action and its quantum. Without Planck's constant, physics could not describe the atomic world. We would have no understanding of chemistry, no explanation of how stars shine, no theory of how the universe evolved from the Big Bang, and it was discovered by a man sitting alone in a study in Berlin, desperately trying to solve a problem about heated cavities. A man who endured losses that would break most people. A man who maintained his dignity and continued his work even as his world crumbled around him. Consider the improbability of this. That personal catastrophe and scientific triumph could coexist in one life. That the physicist who revealed nature's deepest uncertainties was himself certain of his moral duties, certain in his love for his family, certain in his commitment to truth. Max never fully accepted the quantum theory he founded. He spent decades hoping to find a way back to classical determinism, to continuous change, to a universe that operated by strict causal laws. He never succeeded. Nature refused to cooperate with his preferences, but his discomfort with quantum mechanics does not diminish his achievement. He discovered something true even though he wished it were not true. He followed the mathematics wherever it led, even when it led to conclusions that violated his deepest intuitions about how reality should work. This is the mark of genuine science. Not confirming what you want to believe, but accepting what the evidence demonstrates, even when it troubles you, especially when it troubles you. In 1947, Planck is invited to give lectures, to attend conferences, to be honored by the scientific community. He is too frail to travel much, but when he can, he goes. He speaks about thermodynamics, about the nature of physical law, about the relationship between science and philosophy. He never speaks about the losses he has endured, never mentions his children in public remarks, never dwells on the horrors Germany inflicted upon the world. Instead, he talks about eternal principles, about the laws of nature that hold regardless of human events, about the search for truth as humanity's noblest calling. Some see this as denial, an old man unable to face his grief, but perhaps it is something else. Perhaps Max understands that personal suffering, however intense, is not the whole story, that his individual tragedies, and even Germany's collective tragedy, do not negate what he discovered. That truth exists independent of human pain. The universe is indifferent to our suffering. It operates by laws that care nothing for our hopes or fears. Stars fuse hydrogen into helium through quantum tunneling whether we are happy or sad. Electrons occupy discrete energy levels, whether civilizations rise or fall. Planck's constant remains constant through war and peace, through birth and death, through all of human history. This is not comforting in the way we usually seek comfort. It does not ease grief. It does not restore the dead. But it offers a different kind of solace, the solace of meaning, of having contributed to human understanding, of having discovered something that will outlast all the pain. On October 4th, 1947, Max Planck dies in Göttingen. He is 89 years old. He has lived through the unification of Germany, the First World War, the Weimar Republic, the Nazi years, and the Second World War. He has seen physics transformed from classical certainty to quantum uncertainty. He has buried 4 children, outlived 2 wives, witnessed the destruction of German science and German culture, and he has given humanity quantum mechanics, the key to understanding reality at the smallest scales, the foundation for technologies that now define modern civilization, a constant that appears in billions of calculations every second in devices across the planet. His funeral is small. Germany in 1947 is struggling to survive. There is little energy for grand memorials, but scientists across the world mark his passing. Einstein in America writes of Planck's courage and integrity. Bohr in Copenhagen honors the man who started the quantum revolution. Max von Laue, his oldest friend, speaks of a life devoted to truth. Planck is buried in Göttingen. His grave is simple, but his legacy is immense. Think about what he showed us. That at the deepest level, nature does not flow smoothly but jumps, does not determine but calculates probabilities, does not reveal but conceals until observed. That reality itself has a fundamental graininess defined by his constant. This was not what anyone expected. Classical physics assumed that with sufficient information, everything could be predicted, that the universe was like a vast clockwork, its every motion determined by initial conditions and physical laws. That randomness was merely a reflection of ignorance, not a fundamental property of nature. Planck's quantum destroyed this comfortable picture. Uncertainty is not ignorance, but reality. You cannot know both position and momentum with arbitrary precision, not because your instruments are insufficiently accurate, but because particles do not have both properties simultaneously. The universe at quantum scales is fundamentally probabilistic. For a man who valued order and certainty, who chose physics for its eternal truths, this was deeply troubling. Yet Max accepted it because the evidence demanded it. Because nature, when carefully questioned through experiment, gave quantum answers. His life teaches something beyond physics. It teaches that meaning can survive loss, that the search for truth can sustain the human spirit even when everything else fails, that what we discover, if it is genuinely true, transcends our personal circumstances. Max Planck's children died, but his constant lives, his Germany was destroyed, but his discovery rebuilt civilization on quantum foundations. His world collapsed, but his equation revealed a deeper world where reality operates by rules he was first to glimpse. This is not to say that scientific achievement compensates for personal tragedy. Nothing compensates for the death of a child. No discovery erases that pain. Max's grief was real and justified and immense, but alongside the grief, there was also this. He had touched something eternal, had added to human knowledge in a way that would never be lost, had discovered a fundamental constant of nature that will remain true for as long as the universe exists. Every time a quantum computer performs a calculation, Planck's constant is at work. Every time sunlight generates electricity in a solar panel, his photoelectric equation determines the process. Every time an LED emits light, his relationship between energy and frequency defines the color. Every time an MRI scanner maps a brain, his quantum mechanics reads the spin of hydrogen nuclei. The modern world operates on quantum principles. The technologies that define our era, that connect us globally, that have extended human lifespans and capabilities, all trace back to the equation Max Planck presented on December 14, 1900. And beyond technology, there is understanding. We now know that reality is stranger than our ancestors imagined, that matter and energy are quantized, that observation affects what is observed, that at the smallest scales, the universe is irreducibly uncertain. These insights have philosophical implications that extend far beyond physics. They suggest that reality is not fixed, but participatory, that the universe does not exist as a predetermined script, but unfolds through interactions, through measurements, through the actualization of possibilities. Whether this means consciousness plays a fundamental role remains debated, but it certainly means that the sharp distinction between observer and observed, between subject and object, breaks down at the quantum level. We are not separate from the universe we study. We are part of it, and our act of studying changes what we study. Planck opened this door, reluctantly perhaps, against his preferences certainly, but once opened, the door could not be closed. The quantum realm lay revealed, and humanity had to learn to think quantum thoughts, to accept quantum uncertainty, to build a quantum civilization. Now, decades after Max's death, his constant appears in unexpected places. In the information-theoretic foundations of physics, where some researchers suggest that reality is fundamentally about information rather than matter. In theories of quantum cosmology, where the Big Bang itself is a quantum event. In discussions of whether the universe is a simulation, where Planck length might represent the grid size of ultimate reality. His constant has become more than a number. It has become a symbol, a reminder that beneath the apparent smoothness of everyday life, there is quantized structure, that nature has a fundamental discreteness we cannot eliminate. That reality at the deepest level is not what common sense suggests. And perhaps there is poetic justice in this. Max Planck, who lost so much, who endured such discontinuous catastrophes, discovered that nature itself is discontinuous, that at the quantum level, smooth change is impossible, that reality jumps. His life was marked by jumps, from joy to grief, from family to loss, from peace to war. There was no gradual transition from having a son to not having a son. Irwin was alive, then dead. The change was discrete, quantum, discontinuous. Did this prepare Max to accept quantum jumps in physics? We cannot know, but we can note that a man who experienced radical discontinuity in his personal life discovered radical discontinuity in nature. The universe is quantum. Energy comes in packets. Reality is granular. And these facts were revealed by a human being who maintained his dignity through unbearable loss, who continued his work when continuation seemed pointless, who discovered eternal truths while living through temporal horror. This is Max, Planck's legacy. Not just a constant, not just an equation, but an example of intellectual courage, of personal integrity, of devotion to truth, even when truth offers no comfort. He played Bach on his piano in war-ruined Göttingen. The music was mathematics made sound, order made beautiful. It reminded him that structure exists, that patterns persist, that some things remain true regardless of circumstances. And his constant, that impossibly tiny number, is the same kind of truth. Not beautiful in the way music is beautiful, but beautiful in its universality, its eternality, its indifference to human affairs, coupled with its centrality to human understanding. 6.6, 6 times 10 to the minus 34th joule seconds. The quantum of action, the fundamental unit below which nature refuses to be divided. This is what Max Planck gave us. This is what survives him. This is what will remain when all of us, and all our civilizations, have turned to dust. The constant is eternal, and that perhaps is enough.